We have Carlo Cepollaro. All set up.
Okay, can you hear me?
No.
Now?
Yes.
Better.
So whenever you are ready.
Okay. So, first of all, thank you very much to the organizers for inviting me here. And also thanks to all of you to be here on the last day after a conference dinner, free online talks. I know it's hard. So I think I will talk about something slightly different from what we heard this morning in a, let's say, different direction. So I will talk about Einstein's equivalence principle and a way to generalize it to quantum mechanical effects using quantum reference frames. So this also connects to what Luca Appadula talked about yesterday. So I will also give a refresh of what he talked about if you were not there or if you want to hear it about it again. And yeah, let's start. So it doesn't work. Yes, it does. A little bit of motivation. So there are so many claims about what is the role of the equivalence principle in quantum mechanics. These are just a few papers that I randomly picked from arXiv. There are so many different positions. So for example, if you believe in a collapse model in which gravity is fundamentally incompatible with quantum mechanical effects and quantum mechanical effects will disappear, of course, you will think that the equivalence principle breaks down. On the other hand, depending on which type of equivalence principle you're thinking of, because there are different types, you will say that it could or it could not apply to quantum mechanics, or it should be modified or not modified to be true in quantum mechanics. So I would like to start by saying that I think it is very important to try to understand the role of the equivalence principle in quantum mechanics, in the sense that the equivalence principle has been foundational for general relativity. So try to construct an intuition, a theoretical intuition on what are the quantum mechanical effects related to the principle can lead us to a theory of quantum gravity. And if not a theory of quantum gravity, at least to predict some effects that we can see in some low energy, maybe tabletop experiments. And this is what I want to talk about today. So I would like to start talking about different classical equivalence principles because there are many of them. I would like to collect them in 3 classes, but there are actually more. So if you're interested, there is this reference in which they analyze different definitions of equivalence principles. But let's talk about just 3 of them. And one of them is the weak equivalence principle, the Galilean one that was also used by Newton. Then there is Einstein's equivalence principle, and then there is strong equivalence principle. In my talk, I will focus on Einstein's one, but I will give you definitions for every of them. So the weak equivalence principle is the oldest one, due to Galilei, and it is the universality of free fall. So we can think of it as we have 2 test bodies, and their trajectories, when they freely fall, do not depend on their composition. This is a possible definition. But it's not the only one. Now, if you have Newtonian mechanics and we know that the force equals the mass times the acceleration, we can say, well, then this means that the inertial mass equals the gravitational mass. These 2 simplify, and then we get that the acceleration equals g. And these 3 things, inertial mass equals gravitational mass, universality of free fall in the sense of trajectories, and acceleration equal the gravitational acceleration, are actually 3 different things in quantum mechanics. So I will talk about it in a second, but this is just to say we have to be careful in even in our interpretation of the principle. And something that is related to it is Newton's bucket experiment. I don't know if you heard of it, but it is a thought experiment. So Newton imagines that he has a bucket and there is some water in it. And at first the situation is static, nothing moves. And so the water is still with respect to the observer and also with respect to the bucket. And then the bucket starts rotating, and also the water starts rotating. And then at some point, the water will rotate with the same rotational speed as the bucket. And due to tension effect, there will be some concavity that the water forms. Now, if we describe the situation from the accelerated reference frame, from the rotational frame of the bucket, there will be no relative motion between the bucket and the water, because they're both rotating with the same speed. But nevertheless, we will see an effect of motion, because we will see this concavity that was not there before. So this is an argument for which Newton can say that motion is somehow absolute. There is an absoluteness in motion because we see effects of motion even when there is no relative motion between bodies. So he uses this idea to define his notion of inertial frame. For Newton, acceleration is absolute. It's something that we can just, if you give me a frame, I can tell you whether it is inertial or not in a very absolute sense. It's not inertial with respect to another frame. And so Newton is thinking about this existence of a fixed space with respect to which we can define inertiality. Now, there have been some objection to this kind of reasoning. The most famous one is due to Mach in his famous Mach principle. Now, there is no Mach principle. There are like 20 of them, so it's a bit hard to define what it means. But we can think of it as saying, Mach is saying, well, actually what defines inertia is not something that is absolute, but you can think of it as a definition through the rest of the universe. It is somehow the rest of the universe in a very vague sense that he did not like clarify in a mathematical term, but that defines what inertia is. And in particular, he was talking about the fixed stars, so he was talking about mass. And this was inspirational to Einstein, in the sense that Einstein understands that the inertia and the gravitational field are the same object. So what is inertial and what is not is decided by the gravitational field in that point. So Einstein understands that the inertial frames are not the frames that are inertial with respect to a fixed space, but they are actually the freely falling frames. This is what he calls my happiest thought. And this is the idea that lies behind the Einstein's equivalence principle. So this is the definition that is in Gravitation, the big black book. I will read it out loud because it's very important. In any and every local inertial frame, anywhere and anytime in the universe, all the non-gravitational laws of physics must take on their familiar non-relativistic form. So what Einstein is telling us is that if we are in a freely falling frame that is inertial, we know that geodesics are straight lines. So we see no inertial forces, of course, and then we can change frame. We can make a diffeomorphism change coordinates, and I will have a geodesic equation that suddenly has some tidal forces, some non-inertial forces that are due to these Christoffel symbols, and we have this metric that is Minkowski, but changed with the diffeomorphism. Now, what Einstein is telling us is that we have to take these things very seriously. So these Christoffel symbols can be replaced by the Christoffel symbol due to a metric that is not just a change of coordinates, it's not just tidal forces, but it is gravity. So what Einstein is teaching us with this principle is that gravity is inertia in this sense. Okay, so there are three different aspects of Einstein's equivalence principle. The first one is the weak equivalence principle, the one that I was naming before. But there are also two other of them. One of them is local Lorentz invariance, which is a statement about the validity of special relativity in local frames. And then there is local position invariance, which is a statement about the indistinguishability of freely falling frames depending on their position. The effects should not depend, the local effects should not depend on the position in space-time. These three of them are equivalent to the Einstein's equivalence principle. There is also another version of the equivalence principle that is the strong one. I will not talk about this, but this is just to say that the Einstein's equivalence principle talks about test bodies in local inertial frame, but we can try to extend this to also massive bodies that self-gravitate like stars. And the strong equivalence principle is addressed in this kind of scenarios. But I will focus just on the Einstein's one. Okay, so this is just to say that if we try to think about the role of equivalence principles in quantum mechanics, we have to be very careful. So just focusing on the weak equivalence principle, we can get different conclusions based on what is our interpretation of the weak equivalence principle in quantum mechanics. So for example, if we think that the weak equivalence principle is teaching us that the trajectories of freely falling bodies are independent of their composition, well, this cannot be true in quantum mechanics. We don't have trajectories. What does it mean? On the other hand, we can also interpret it in another way. We can say the equations of motion of freely falling bodies do not depend on their mass. But this is also false in quantum mechanics. If you take a freely falling particle, the dynamics will depend on the mass, for example, the spreading of the wave function. if on the other hand you interpret it saying that the equations of motion under constant gravitational field are indistinguishable from the ones with constant acceleration, then this is true in quantum mechanics. If you take the equations, you will see that this is correct. So you have to be careful even in your interpretation of the principle, not only in which principle you choose. And now I would like to claim that there is a way to define a new principle using this concept of quantum reference frames that are clearly very important. Like reference frames, classical reference frames are very important in defining the equivalence principle, so it might make sense to try to understand what a quantum reference frame is and how we can use these concepts. So a little bit of motivation that led this kind of research. So when I think of reference frames, I think of a set of axes. I think of a x-axis, y-axis, z-axis, and some time axis. Or if you want, also in less dimensions. But this is, of course, just an abstraction. We do not see axes in reality. In reality, if I go to the lab, I'm not an experimentalist, but if I went to the lab, I would find there maybe some objects, some rulers, or some clocks, with respect to which I define my quantities. So in reality, the reference frames are actually physical objects. And these physical objects must obey our physical laws. Now, here I'm making an assumption, and the assumption is that quantum mechanics is universal. So in this sense, some of you might disagree. So I'm assuming here that there is no collapse. Quantum mechanics holds at any scale. And I'm assuming this because, as far as we know, it does. So if we believe that physical objects obey quantum mechanics, and if we believe that reference frames are physical objects, then we should believe that reference frames should have quantum properties. And then it makes sense to ask questions about what are the quantum properties of reference frames and how we can describe things from quantum reference frames. So, for example, one question that you might ask is, if I have a ruler that is in superposition of different locations, can I still describe position with the perspective of this ruler? Does it make sense? And if so, what is the position that it describes? And then I can ask also something else. I can take a clock. If I take a clock and I put it in superposition of different heights in a gravitational field, I know that there is time dilation. So the time will flow differently at the two heights, but can I still describe time with respect to this superposed clock? So these are the kind of questions that are interesting in these scenarios. And I would like to claim that this is at least partially motivated by experiments or hopes that we have from experiments. So if you remember what Markus Aspelmayer was talking about in the very first talk of this conference, he was talking about the measurement of gravitational fields of very small objects. So what he wants to do in the next 20 years is try to find the gravitational field of smaller and smaller objects, hoping at some point that he will measure the gravitational field of objects that can have quantum properties that are so small that can become quantum. So on the one hand, we are measuring smaller and smaller gravitational fields, and on the other hand, we are putting in superposition bigger and bigger objects, or at least bigger and bigger superpositions. So this is an experiment by the group of Kasevich. Tim Kovacs was also speaking. So in this experiment, they have this half-meter scale superposition. They have objects that can superpose at somehow macroscopic scales. So if these two regimes merge, if we manage to find a regime in which we can put in superposition masses such that we can measure the gravitational field, then we cannot use classical reference frames anymore to describe this situation, because I will have a sort of quantum space-time, and then I will need quantum reference frames to describe it. Okay, so quantum reference frames is an old idea. It was introduced for the first time in the 60s by Aronov and Susskind. This is just to say a little disclaimer. So what I call here quantum reference frames is not that. They have the same name, but there are two different things. What I'm describing here is a concept that was introduced in 2017, and there's a little bit of literature about it in the last years. So as you can see, there are many papers. There are not all of them. And I highlighted in blue the ones that talk about gravity. So as you can see, the first ones were a little bit about the formalism, and the very first one had already mined gravity. But in the last 2 years, there has been a lot of focus on quantum reference frames and gravity. So if you're interested, you might check that. Okay, so now I will give a pedagogical introduction somehow, brief but pedagogical. Also repeating some of the ideas Luca was talking about yesterday. So let's imagine a classical reference frame transformation. So we have three classical systems. Here I'm putting cats, but please ignore them, it's just for notation. We have three classical systems, A, B, and C. And we are describing the position of these three classical systems from the point of view of A, from the reference frame, classical reference frame of A. Now, of course, A will assign itself position 0, and then let's say it assigns B position x1, and it assigns C position x2. Now, if we want to make a classical reference frame change, what we can do is simply translate everything. So from the point of view of B, it is B that is in the 0 position, and now A is in minus x1, and C is also translated correspondingly, as you might, I'm sure you know. Okay, let's talk about now another situation in which B is in a quantum superposition of different locations. And this is the tricky part, like, can I still describe the point of view of B in this situation, even if it is in a quantum superposition? And then one might think different ideas, but one of them is the simplest one. We just do in each branch what we would do classically. So it's just a quantum superposition of classical transformations. So in each branch, I just translate, as I just did in the previous slide. But if I do so, what I get is an entangled state. And please notice that in both frames, if, like in the frame of A, the reference frame, the state of A is 0, and in the frame of B, the reference frame of B is 0. So this can be taken as a definition of what is the reference frame of B. B always assigns 0 to itself. And then you notice that in the first frame, B was in superposition, but now is not anymore. So with quantum reference frames, we can describe the situations in which an object was in superposition first, then you change frame, and it is not anymore. And this can be very useful, as I will show later. Moreover, since this 0 is just is somehow a redundancy of my description, I can just forget about it. Like in every frame, the system will describe itself in 0, so it does not really add any information. And just for actually aesthetic reasons and shorter formulas, I just forget about it. Okay, so here I gave an example of what a quantum reference frame transformation is for translations, but actually the formalism is very general. I can define quantum reference frame transformations for any locally compact group, G. I will not go into the details here, but this is just to say, if you give me a locally compact group, and if you give me an Hilbert space that is big enough, I can always define an ideal quantum reference frame, which means that I can always distinguish two states that are different. This is ideal. Then there are also not ideal frames, but it's a bit more complicated, and I will not talk about that. So as you can see, this the definition of quantum reference frame change, this S unitary transformation. So forgot to tell, it is a unitary transformation, and it is a quantum controlled transformation. So based on the state of A, I apply the classical transformation on the others. So in this sense, it is a quantum controlled classical transformation. And as I was showing before in the experiment, we started from a state that has some coherence, so some superposition in B, and then we ended up with a state that has some entanglement. So what this is teaching us is that coherence, so superposition, and entanglement are frame-dependent features. They do change when a quantum reference frame change, and this is something that we can use in gravity. I will talk about it later. And then there is also a recent result we just put on arXiv, showing that actually the sum of coherence and entanglement is conserved under any ideal quantum reference frame change. And this is also very interesting because it's kind of saying that coherence and entanglement are the same resource in different quantum reference frames. They transform into each other just by changing the viewpoint. Okay, but let's talk about gravity more, because I guess you're more interested in that. So let's talk about a quantum weak equivalence principle that uses quantum reference frames. So, as I was saying, there are many ways of formulating the weak equivalence principle. One of them is that the physical effects seen in a uniform gravitational field are indistinguishable from those seen from a system in constant acceleration. And then a little bit of a pedantic way to talk about it is I can take two particles, A and B. I can make A freely fall, and I can make B just be free. And then I can describe the motion of B from the point of view of A. I can change classical reference frame, go to the classical reference frame of A, and describe the motion of B. What I find is that B is moving according to A with an acceleration that is upwards, and it is exactly equal to minus G. So this pedantic verification in classical mechanics, this Hamiltonian sort of classical of the weak equivalence principle. Now, of course, if I want to do a quantum weak equivalence principle, I can try to think of something similar. So the quantum weak equivalence principle in this scenario says that the physical effects seen in a superposition of uniform gravitational fields are indistinguishable from those seen from a system in superposition of accelerations. So it is a principle that relates not the parameters, acceleration and gravitational acceleration, but the operators. So it is a weak equivalence principle that is true branch by branch as the quantum reference frame transformation. And then I can try to apply the same pedantic idea. So I have, again, two particles. One of them falls in a superposition of gravitational accelerations, and then I want to describe the reference frame of this particle, and I want to see how B moves in this frame. But to do it, I need quantum reference frames, because this particle is moving in a superposition of accelerations. So what I can think of is, I take an Hamiltonian, let's say a classical Hamiltonian for now, the Newtonian potential, and then I make a piecewise linear approximation. So I focus on two different positions, and in these two different positions, I have two different G's. And then I quantize it. Then, for example, I can take the state of A to be in superposition of different heights, and at these two different heights, I have two different gravitational accelerations, respectively G1 and G2. And now I can make, so A is evolving in a superposition of two gravitational accelerations. And now I can make my quantum reference frame change. I can go to the reference frame of A, as I was showing before. And of course, also the Hamiltonian change. This is a unitary transformation. And I can study the dynamics of B in this frame. And what I get is that the acceleration that B undergoes is exactly equal to minus G that I defined before. So what I find is that when A falls in a superposition of gravitational accelerations in the quantum reference frame of A, in the quantum reference frame of A, B evolves in a superposition of accelerations. So this is the quantum weak equivalence principle with quantum reference frames. Sorry, it's the blue, it's this blue thing. So as you can see, that is M acceleration position of B. So yeah, so if this would be classical, that would be the definition of acceleration, but these are operators, and then it's the quantum definition of the acceleration operator. All right, but then we can say much more. We shouldn't just focus on the weak equivalence principle. We can also try to talk about the most general one, the Einstein's equivalence principle. So I showed you before the definition of Einstein's equivalence principle, and this relies on the definition of local inertial frames. And since now we are interested in quantum reference frames, it makes sense to try to understand a little bit better what a local inertial frame is. So what is a local inertial frame? Well, I know that if I take a point on my manifold and I have a metric at that point, I can always make a change of coordinates, a diffeomorphism change. So I make basically a translation and a stretching, such that at that point, locally, the metric is locally flat. So this is what a local inertial frame is. Let's consider now a situation in which, again, assuming universality of quantum mechanics, I have a mass that is in spatial superposition, and this mass generates a gravitational field. Now, the gravitational field will be different in each branch, so what I get is that the gravitational field gets entangled with the mass. And now if I have an object, let's say a clock, that evolves in this scenario, also the evolution of the clock will be different in each branch. So also the clock will get entangled with the original mass. Now, I'm in this scenario, and I want to define a sort of local inertial frame for this clock. Of course, I cannot do it classically because it is in a quantum superposition, but what can I do is using quantum reference frames. So the definition is that the quantum local inertial frame of the clock is a frame that is associated to the quantum particle, where the metric is locally flat and well-defined in the sense that it is not superposed. So before I had a superposition, I make a quantum reference frame change. I don't have the superposition anymore, and I require that it is locally flat in the same classical sense as before. And now with this tool, I can define a quantum Einstein's equivalence principle. And it is just the Einstein equivalence principle as before, but for quantum local inertial frames. So in every quantum local inertial frame, I have basically special relativity and whatever non-gravitational laws I know. Exactly as before, where I had 3 different aspects of the Einstein's equivalence principle, even here I have 3 different aspects of the quantum equivalence principle, sorry, quantum Einstein's equivalence principle. And the first one is the quantum weak equivalence principle I defined before. So we find it as a particular case, let's say. And then I also need to ask that in any quantum local inertial frame, special relativity holds, and that the outcome of any local non-gravitational experiment is independent of the position of the quantum reference frame in which it is performed. So now I will focus a little bit more on the last of these 3 aspects, because it is easier to understand, but we did work on all of them. And in particular, we want to show that it is at least in principle possible to use some technology to test these Einstein's equivalence principle for quantum reference frames. And then, of course, when you want to build your experiment and you try to think, how can I test this quantum equivalence principle? The first thing you can ask yourself is, well, how do I test the classical one? Maybe I can get some inspiration. And there are some prototypical tests of the classical Einstein's equivalence principle, and these tests want to verify the 3 aspects separately. So, for example, if I want to verify the weak equivalence principle, what I do is just I check that the inertial mass equals the gravitational mass. So I check that objects fold in the same way. If I want to test local Lorentz invariance, I can test special relativity. If special relativity doesn't hold, then local Lorentz invariance doesn't either. And if I want to test local position invariance, then the paradigmatic test is the gravitational redshift experiment. So the gravitational redshift experiment, as I'm sure you know, is an experiment in which I have 2 clocks at 2 different heights in a gravitational field, and then I check that the frequency of these 2 clocks, so the time that is measured by these 2 clocks, is different. And then I have a prediction, and this prediction is that the difference in frequency over the average frequency is equal to the difference in gravitational potential over c squared. Now, how do I go from local position invariance, that means that the outcome of experiment in every freely falling frame does not depend on position? How do I go from here to saying that this predicts this delta v over c squared factor? Well, what you can do is take a local inertial frame that is freely falling and momentarily at rest with respect to 1 clock. Then this clock emits a photon, and then you take another frame. This second frame is associated to the second clock, and you take it momentarily at rest with respect to the second clock when the photon arrives. If you do so, you can compare the velocities of the 2 frames, and you learn that they're related through a Lorentz boost. And this Lorentz boost has an effect, Doppler effect, and this Doppler effect gives you exactly this frequency shift. So this is how you go from local position invariance, which seems a little bit of an abstract concept, to an experiment that can tell you how do I measure local position invariance. And what you can practically do is, assuming that local position invariance is false, so you assume that the proper time of the clock in the local inertial frame can depend on position, and then you see what is the prediction. And the prediction is that this delta v over c squared has a correction, and this correction depends on the position of the frames. So this is how you classically test local position invariance. Now, how do we do it quantumly? Well, if we have a similar situation as before, but now these clocks are in superposition, I want to do the same. I want to assign a local inertial frame to one of the clocks. I cannot, because it's in quantum superposition, so I use quantum reference frames. And with quantum reference frames, I repeat the exact same reasoning I just said. And as a result, you find that if quantum local position invariance is violated, then you must have a parameter that now becomes an operator. So there is an operator correction to this frequency shift, and then now you can measure this operator. So if you manage to measure this operator, so the frequency shift between these 2 superposed clocks, then you can check whether quantum local position invariance is correct or not. So how do you practically do it? Well, we had in mind here a simple model, which is somehow an effective model, in which we just have Newtonian quantum mechanics and the first special relativistic and general relativistic correction to time dilation. So this model was used by Lammerthal in '96, and then again in other papers by Zick et al. And the idea is that we are using atomic clocks, as I was mentioning before. So we have external degrees of freedom and also internal degrees of freedom. And the internal degrees of freedom of the atoms are the ones that keep track of time. So they evolve in a non-trivial way in time. And how can you find this model? Well, the easiest thing you can think of is I take Newtonian quantum mechanics, or even Newtonian classical mechanics, let's say for now. Then I take mass energy equivalence. So I'm accounting for the internal energy of the clock in the mass, total mass of the clock. And then I write my Hamiltonian, and then I quantize the internal energy. If I do so, what I get is an Hamiltonian of this form. So what I have is that the first three terms are just the Newtonian standard evolution. Then there is Hi, that is the Hamiltonian that is responsible for the clock, the internal degree of freedom. And then there is a correction to Hi. And this correction is exactly the first special relativistic and time and general relativistic time dilation corrections. All right. So, for example, if you imagine that you have a two-level system as an atomic clock, then you can measure the energy difference between the two levels. And you can see that classically that term is exactly the term that gives you a frequency shift between the energy, and it is the gravitational time dilation and special relativistic time dilation factor I was talking about before. So, okay, so this is the model. We use these atomic clocks. Now, how do we actually test the principle? What we can think of is using this atomic clock interferometry. So the idea is using these atomic fountains in which they manage to put atoms in superposition of different heights, but you need some extra control on them. You also need to control the internal degrees of freedom, put them in a superposition of internal states, and then make them evolve in a non-trivial way, in such a way that you can keep track of time. If you do so, which is, of course, an experimentally hard, but maybe you can do it. If you do so, we show that you can actually measure these and test this principle. So what I'm describing here is this situation in which I have my atomic clocks that are in superposition inside of the interferometer. And this is the state just after the first beam splitter. So you have a superposition in the first frame. In the first branch, you have that the two clocks are up. In the second branch, the two clocks are down. And then you have an internal state that keeps track of time. Now, if you let this system evolve, so if the particles evolve inside of the interferometer, what you get is that the two internal states will evolve and will be different because the time flows differently at the two branches. And then, of course, you also have a phase that is given by the evolution of the external degrees of freedom. So here I just write the formulas while I drink a little bit of water. But they're not really important. The only important thing is that you have some non-trivial evolution in time, and this depends on gravitational and special relativistic time dilation. And of course, we can also make a measurement. So if we measure this kind of Bell state, what we get is some probabilities. And these probabilities depend on the overlap between the internal and the between the internal states up and down. So we are sensitive to this kind of time dilation effects. So now the crucial part is, okay, so we know that we can measure time dilation. Can we measure our principle? And the answer is yes. So for example, here about quantum local position invariance, we know that the time dilation modifies with this alpha x operator factor. So what I can do is drinking a little bit of water. And so since this factor is modified, also my probabilities will be modified, basically. And then by measuring this modified probability, I can understand what are the values of this alpha of x, and so I can test the principle. So, summary. Very good. So there are different definitions of the equivalence principle. Depending on their interpretation, some of them might be or might less be compatible with quantum mechanics. Quantum reference frames generalize classical reference frames for particles that can be in quantum superpositions. Quantum reference frames can be used to define a quantum extension of the Einstein's equivalence principle. And the Einstein's equivalence principle for quantum reference frames can be tested with atomic clock interferometry. And with this, I thank you.
Questions?
Instead of an atomic clock, why not one vibrating molecule or one processing electron with spin through a beam splitter or something like that?
I think whatever is okay, as long as you have internal degrees of freedom that are sensitive to time. If you can measure somehow time and you put them in superposition of different heights, this should work. Another option, for example, is light. You can have photons, and you can do the same.
I mean, that said as a comment, does the cow experiment, in a sense, confirm the quantum equivalence principle or not in your definition?
I think there is debate on this. I would say no. And the reason why I would say so is that the cow experiment uses neutrons, and these neutrons do not, like the internal degrees of freedom are not involved in the evolution. So when you, in these probabilities here, for example, I'm showing that the that evolved state depend on the phases that are accumulating with the external degrees of freedom. And these are the only ones that contribute to the cow experiment. While here we are doing more. Exactly. And it is very important because you can justify these phases just with Newtonian mechanics. While you would want to claim that we have really general relativistic time dilation and special relativistic time dilation, and the only way is really using clocks that are shifted.
More questions? I have one also.
Thanks for the talk. Is there any hope for a quantum version of the strong equivalence principle, maybe using what Luca was mentioning the other day? Yeah.
I don't know. We didn't think about it in the sense that we were trying to predict effects for test masses for small stuff, and then you can try to think of stars in superposition and so on, but one of them is already hard. But in principle, I would say yes.
Questions? I have one. In the beginning of the argument, you say something about the definition of the Hilbert space for the Jew states, and that they have to be, there is something of ideal states are perfectly distinguishable, right?
Yes, so if
yes. So in this kind of situation and the BMV situation and all of the situations that we are considering here in the lab, the gravitational field is a very small perturbation around a very stable background. So like in real situations, this gravitational state is not perfectly distinguishable and it's not ideal. And it seems like
I agree that in general
the quantum reference frame whole argument depends on that to be valid. So how?
Yes and no. So I agree that in general you can have superposition of gravitational fields that are not perfectly distinguishable, and in that case it is hard to do it, and we don't have a framework for that. But for example, you can think of superposition of semi-classical states, and you can assume that these are perfectly distinguishable. This is what Luca was talking about yesterday. So in this case, you can do it. But here, we do have perfectly distinguishable situations. So this is not like BMV. I don't know if in BMV you don't have distinguishability, but here for sure you do have it. And the reason is that we are in this low energy regime in which we are imagining that gravity is sourced mainly or only by position. So we're not taking into account also the gravity effects due to the momentum. And then we can imagine that we have perfectly distinguished states of position for the masses. And then also the gravitational field will be different.
So you would agree that this is a fully semi-classical treatment?
No, no, in the sense that it can be a semi-classical treatment if you want to measure gravitational fields that are sourced by both X and P. But then if you are okay with a gravitational field that is sourced only on X, then you can have perfectly distinguishable X.
Yes.
So I think I didn't understand why the cow experiment is not a test of the weak equivalence principle in the following sense. Quantum field theories in global hyperbolic spacetimes, even for free fields, implies the weak equivalence principle. So if the weak equivalence principle is not observed, this would implies that quantum field theory in curved spacetime is not correct in general. And if you go to the non-relativistic regime, it would imply that the Schrödinger equation with a gravitational potential would not be correct.
No,
But
no, I
this
agree
is-
with you. So
In
just
this sense,
clarify.
you understood, right?
I do think that the cow is a test for the weak equivalence principle. I don't think it's a test for the Einstein's equivalence principle, because you don't have time dilation.
So let's thank our speaker once more. And we will be back 10 minutes past 2. All right. And please scan the QR code and give compliments to our friends at Principia. Or